All right, hello. So today we're going to talk about the rapid fire feature on our digital step attenuators and our digital VGAs. One of the questions that comes up most often when we talk to customers is exactly what is this feature? And so the easiest way for me to describe this is to talk about this hybrid control mechanism. Everyone's familiar with the SPI interface, and everyone should be familiar with a parallel interface, which are commonly used with DSAs. The one thing that we did differently with this device is that we added two registers for the attenuation state itself. A normal DSA will obviously have a register which will hold the 7-bit configuration for the DSA itself. Again, our devices are 7-bit components or DSAs. They give you 31.75 dB of range and quarter dB steps. So when you go and send in a SPI command, you'll program in those 7 bits within the register itself. What we do, this is the primary attenuator that everybody has in their DSAs. We've added a separate feature here. We've added a secondary register. Here's the primary, and then with the secondary, so you send one 16-bit SPI transaction to the first register to hold those 7 bits. Then you send in a secondary 16-bit SPI transaction to program the secondary state. And then what we do is we use one external bit to tell the device to either look at this first register or look at the second. You can toggle back and forth. When you do the toggling, it loads in those 7 bits into the DSA core itself, right? So here's the DSA core representation. So that toggle either tells this register to load or again, this register to load. It's not really tricky, you just understand what we're trying to pull off here. Three primary ones that we've come across. The first of which is a common trick that we play in the cellular domain for base stations. So imagine you've got a receiver. I'll draw this a little better. Here's your antenna coming in. Here's your typical lineup, right? You've got from the antenna, you have an LNA, maybe you have some filtering, okay? And then you maybe have some more stages until you go down, and eventually you're going to have an A to D, right? And with that A to D, you have to make sure that you obviously don't saturate that component. What will happen in the cellular domain for base stations again is you'll receive a signal, and normally, let's say it's a spread spectrum signal, right? We call these a BART head. Sometimes, it's rare, but it does happen, you'll get what we call a rogue blocker. And that rogue blocker might be very, very high in terms of signal strength. And when this rogue blocker, it could be a CW, it could be a tone, maybe it's another subscriber, it could be a multitude of things. Anyway, the system has to be able to provide a provision to accept and account for or be resilient to this blocker. So when this happens and you go through the receive chain, what will often happen is all the signal gets passed along to the A to D, and the A to D, you'll basically rail it. You're going to send it into an overdrive state, and when that happens, you cannot receive anything. You've saturated it. It sees everything as a high, as basically as the again, it's an overdrive condition. So you're at full scale for the A to D, and so you can't receive anything. So what you do, because you can't filter this guy out, what you'll often do is add an attenuator. I don't know, I'm going to place it, it's typically placed like here, or maybe it's a bypass. And with that attenuator, you can quickly switch in attenuation to drive this entire signal. Maybe it'll become like this by the time you're at the A to D. I should probably draw this over here to make it clear. So when you throw the attenuation in, instead of being really high, like this in the normal state, maybe it'll be like this, right? And so you basically stay below the overdrive state of the A to D. You're not at full scale anymore. And at least you can receive the subscribers that are close in. So hopefully that makes sense. Now, another use case, I'm going to switch gears here and talk about on the transmit side of things for a power amplifier. Oftentimes, our customers in the repeater or booster space, you'll have a simple type of application where you have a donor antenna and then you have a transmit antenna, right, for distribution out here. You have some gain stages and so forth. Again, this is a highly simplified plot diagram. Well, what happens if this antenna gets dislodged or taken out? Or maybe the antenna's there, but you've got some guy here that walks in front of the antenna and you cause some feedback loop to occur. In that instance, the PA can get damaged because you're overdriving it. So oftentimes what customers will do is they'll put in a DSA at this place or in this spot. And when this state happens, when you either have a high VISWAR state or the antenna gets disconnected or you have a feedback path that gets developed, you want to be able to cut that gain down very, very quickly. And so the rapid fire allows you to switch from this primary state into the secondary state, which is, let's just make up some number. Maybe the primary state is 5 dB for gain trim, and the secondary state might be 30 dB. So by flipping that one RFA bit, you can throw the attenuation in here, cut the gain down, and the oscillation is basically squashed. The last application, so I'm running out of space here, but the last application is for TDD modes. So again, if you look at like a repeater or booster type of application, and you've got an uplink and a downlink state, right? So maybe, let me put this, I'll try to draw this from memory. You basically have a path for uplink and downlink, and you've got, let's say, a TDD mode, you've got a switch, and I'm gonna just draw it like this. Maybe this is one antenna going here. And again, bear with my poor drawing skills. And we're gonna do it like this again. From here, like this. So with a simple, like a two-way amplifier, if you want, bidirectional amplifier, or like a repeater booster, you've got one state for the uplink and one state for the downlink. That's what happens when you do this on the fly. Hopefully this makes more sense. So again, this is like uplink and this is the downlink state. And perhaps for gain trim, you want to place, a DSA here and a DSA here. Now you've burned up two devices. Well, because you have a common RF path, one advantage you could do is eliminate the DSAs here and instead put one in this common path. And in doing so, you've reduced the chip count by a factor of 2, right? So you use the rapid fire feature to toggle between the primary state. Maybe the primary is the same as the uplink trim, and then the secondary state is the downlink. And again, you just quickly toggle back and forth between the two. So anyway, these are the main use cases for the DSA, for the rapid fire function. Hopefully this is helpful. If you have any questions, please reach out to our applications team. It's pretty simple, applications@guerrilla-rf.com. Thank you for your time.
Thank you so much for watching. If you'd like more information, please email us at sales@guerrilla-rf.com. And don't forget to subscribe to our channel for more content from Guerrilla RF.